There are students right now taking the digital SAT and solving every math question by hand like it's 1837. No Desmos, no strategies, just pencil scratches, panic, and the quiet feeling of, I think I just ruined my future. And look, I respect it, but if you're doing every SAT math problem by hand, you're basically showing up to a Formula One race on a donkey. A brave donkey, a hardworking donkey, but still a donkey. I've taught SAT math for 10 years, and the biggest mistake I see is students treating the digital SAT like the old paper SAT. This is not a Shakespeare class. You do not get extra credit for suffering. So in this video, I'm showing you the 7 Desmos tricks every SAT student should know before test day. And the 7th trick at the end can save you when a hard Module 2 question looks like it was written by a sleep-deprived wizard. So go ahead, open Desmos, cancel the emotional breakdown, and let's cook. Oh wait, no, not that kind of cook. Let me try again. Let's cook. So the first trick is on table regressions, and there's usually about 3 of these on every single SAT. So if you learn this trick, that's automatically about 30 additional points that you're gonna get. So for this question right here, it says that the table shows 4 values of x and their corresponding values of f of x. There is a linear relationship between x and f of x that is defined by the equation f of x equals mx minus 28, where m is a constant. What is the value of m? Any time that you are given a table of values and you are asked to find the equation or part of the equation, all you're going to do every single time is you're just going to take that table, going to go to Desmos, and you're going to hit the plus button right here. You're going to add a table, and on that table you're going to input all of your values. Then you're going to tap this button right here that says add regression. Once you hit add regression, Desmos is going to go ahead and connect your points, but not only does it connect your points, it also gets you an equation, in this case 11x minus 28. They were asking me for m, which is the one in front of x, so in this case, my answer is just 11. Now you have to be careful, there's a little bit of a caveat over here because Desmos is always going to default to a linear regression. So if I'm dealing with a quadratic or something that's cubic or quartic or a square root, I'm going to have to change that. But in this case, I'm dealing with a linear relationship, so I'm good, I'll leave it, but just watch out for that in the future. For this one, I'm done. My answer is 11, and I was able to do that with no math and just by using table regressions. Here's another variation, and this one is a little bit different because you're not directly given a table of values or a bunch of points. Over here, it's a word problem, and it says that the quadratic function g models the depth in meters below the surface of the water of a seal t minutes after the seal entered the water during a dive. The function estimates that the seal reached its maximum depth of 302.4 meters 6 minutes after it entered the water, and then reached the surface of the water 12 minutes after it entered the water. Based on the function, what was the estimated depth to the nearest meter of the seal 10 minutes after it entered the water? So what I can do over here is I can kind of decode the word problem in order to get my points out of it. The first one is super obvious. It's 6 minutes for 302.4 meters, and I see that t is minutes, so the t is like my x in this case, so my x would essentially be 6, so my first point is at 6, comma, 302.4. I'm going to skim for other numbers, and I see another number over here, which is 12. So at 12 minutes, I am at the surface. So here's the surface of the water. If the function is measuring the depth below the surface, then at the surface, I must be at 0. That's 0 meters below the surface, right? So my second point is going to be 12 comma 0. But 2 points is not enough to make a quadratic function, because how is Desmos going to know whether your parabola opens up or your parabola opens down, right? So because of that, I'm going to need 3 points. So I'm going to dig a little bit deeper over here, and I see something that kind of catches my eye. After the seal entered the water during a dive, right? So when does the seal enter the water? It's going to enter the water at 0 minutes, right? So as soon as it enters the water, no time has passed. That's 0 minutes. And where does it enter the water from? It enters the water from the surface, right? It's not like it can enter the water 300 meters below the surface. That makes no sense. So if it enters the water at the surface, then my depth below the surface is going to be 0. So I was able to infer my third point just digging a little bit deeper into the problem. All right, so now that I have 3 points, I can just go to Desmos and I can add a table, and then I can input those values into my table. I'll get my points right here. I will tap add regression, but when I add my regression, I need to be careful because this is a quadratic function. So I need to tell Desmos that I'm dealing with a quadratic regression. So now I can correctly connect the points and give me the proper equation. And this question is asking for the depth of the seal 10 minutes after it entered the water. So I'm looking for an x value of 10. So all I need to do over here is I'll go to the next line. I will type in that x equals 10. I will see where it hits the graph. I see that it hits the graph at 10, 168. Therefore, my depth And my answer to this question is going to be 168. The second trick is going to be for solving one variable equations. There's usually about 3 of these every single test, meaning if you know this trick, that'll get you about an extra 30 points. So now we're at about 60 total points. Now, the very first thing to understand for this section is going to be how Desmos differentiates between equations and expressions. So if I plug in an expression, x plus 5, Desmos is going to give me the graph of x plus 5, so I see all the combinations of x and y over here. Now, if I change that expression to an equation, Desmos is now going to give me a vertical line of where the solution is, and that tells me that x is 2 over here. So you can see how Desmos operates differently between expressions and equations. For expressions, it gives you the graph. For equations, it gives you the solution. But it will only give you the solution for the equation if there's only one variable in there, because now if I introduce a y and there's 2 variables, it goes back to giving me a graph. So if I ever want to directly get the solution to something, it has to be a one variable equation. So the conditions for Desmos to solve is going to be these 2 conditions. Condition number 1, it's an equation. An equation keyword has an equal sign. So as long as it has an equal sign, it's an equation. And condition number 2, it is one unique variable. So even if I look at this question right over here, I have z squared and z. They are both z. It doesn't matter that one is squared and one is not. Since they're both z, that's one unique variable. Therefore, it follows these conditions. Therefore, I can use Desmos to just solve for it. Now, I have students asking me all the time after I teach them this, and they say, oh, so if it's an expression, then I shouldn't plug it in. Not necessarily. Maybe you should, maybe you shouldn't. It depends on what the question is asking. Sometimes we want the graph, sometimes we want the solution. In this case, I want the solution. So what I'll do is I'll go to Desmos and I will go ahead and plug in that equation. Z squared plus 10z minus 24 equals 0, so I can find the solutions. But Desmos says that we only support implicit equations of x and y. So what's happening over here? Desmos is looking at this and saying, hey, that's a z. I have no idea if that's a constant or if that's a variable. So therefore, I'm just not going to risk it. And I'm going to give them this little caution symbol right over here so I can stop them. So in order to bypass this, you just need to make it clear to Desmos what z is. Z in this case is acting like my variable. So Desmos always recognizes x as a variable. So if I just change z to x, now it'll actually go ahead and graph it, and it'll get me the 2 solutions at 2 and negative 12. So just like that, I got my solutions to this question by simply taking one variable equations and plugging them directly into Desmos. The third trick is going to be on equivalent expressions. There's usually about 1 of these every test. So if you learn this trick, that's an instant extra 10 points. And now we're at 70 total extra points. So whenever you look at a question and you literally just see the words equivalent expression, you're always going to solve it this way. Now, there's 2 methods. So I'm going to cover the first one. The first one has more to do with constants, when your expression has a lot of constants in it and not really a lot of variables or any variables at all. So in this case, I have 42a over k plus 42ak, and I need to find the equivalent one. Well, if I think about it, whichever one is equivalent, let's just say it's b that's equivalent. If b is the equivalent one, then for any value of a and for any value of k, they should be coming out to the same number, right? Because they're the same expression. Well, luckily with the power of Desmos, I can test it out for pretty much any value of a and any value of k that I want. So all I'm going to do over here is I'm going to go to Desmos and I'm going to plug in all of them. I'm going to plug in the original one from the question as well as all 4 answers. Some of you guys might be thinking right now, oh my God, am I really going to spend a whole 1 or 2 minutes plugging all of these in? Well, you can be smart about it, and you can take the first one and copy paste it over, then just put the k squared. Take this one, copy paste it over, then just put the k squared, because they're pretty similar, so that can save you a little bit of time. But anyways, after you have them all plugged in, you're just going to go ahead and put in your sliders. So when A is 1 and K is 1, I noticed that all of them come out to 84. That sucks. Now, SAT does this on purpose. SAT knows that you're going to go and plug in a 1 for A and a 1 for K because everyone is used to plugging in 1. It's the easiest number to plug in, and it's the fastest number to plug in. So SAT tries to prevent students from doing that, but we're smart. We know how to use Desmos. We know all these tricks, so we can get a little bit of an edge on the SAT. SAT makes it so that, we can't get away with just plugging in 1, but I can plug in weird numbers. I can plug in 4.3 and 3.4. So now I have a little bit of an edge on the SAT, right? The one from the problem comes out to 667. The only other one that comes out to 667 is going to be answer D. So just like that, I got my answer by just plugging them all in and testing values of a and k in Desmos. Now, that was the first method when they're constants. So here's what to do when you have variables. So in this problem, I'm given this equation for f of x, and then I'm told that it can be rewritten just like this. So the fact that an equation can be rewritten kind of reminds me of equivalent expressions. It's just another way of writing it, meaning they have to be equivalent, they have to be the same thing, right? But in this case, it's not a and k that I'm testing out a bunch of different values for a and k. In this case, it's literally two different graphs, two different functions. So, well, I'm sorry, I shouldn't say different, but two separate functions. So therefore, whatever graph I get for this one, which is going to get me like an exponential curve just like that, the graph for this one should get me that same exact exponential curve, right? So what I'm going to do is I'm going to go ahead and I'm going to take both of them and plug them both into Desmos, and I'm going to add a slider for p. So now I'm looking for a value of p that's going to get these two graphs to be the exact same. I don't need to use a slider because this is multiple choice. I have literally 4 options. So I'm going to try the first one, which is 16. That looks pretty good, but they're off by a little bit. Let me try the next one, 21. That's way too off. Let me try 46. That doesn't work. Let me try 96. That doesn't work either. Closest one was 16. And the question literally says, which of the following is closest to p? So my answer is A. So again, anytime you guys see anything along the lines of equivalent expressions, equations being rewritten, or anything of that nature, you're always going to solve it using one of these two methods, either using sliders for your constants to test it out at various values for your constant, or plugging in the actual graphs to get the graphs to match up. For the fourth trick, we have systems of equations. There's usually about 2 of these on every single SAT, so knowing this trick will get you an additional 20 points, so we are now at 90 total points. For any single system of equations where you're looking for the value of y, or the value of x, or the value of x minus y, or the value of 4x plus 3y, whatever, so long as they want you to solve the system of equations, please do not ever use substitution or elimination. It is a massive waste of time, because for a system of equations, the first one is going to make a graph, the second one is going to make a graph, and you're looking for the one solution that makes both of them true simultaneously. That is also known as your intersection point. How can we find that intersection point? Easy, Desmos. We plug both of them in, we find the intersection point. Let me just zoom in a little bit more. Find the intersection point, it's right over there. They're looking for the value of y, that is going to be 1. And just like that, we got our answer. So every single system of equations, plug it straight into Desmos. Please do not ever do substitution or elimination. Trick number 5 is going to be on quadratic equations. These aren't super common. There's anywhere between 0 to 1 per test. So knowing this trick gets you about 5 additional points, so we are now at 95 total points. So over here, I'm given this equation, and I'm told that the solution can be written in this format: 8 minus square root of k over 4. Well, what does that remind you of, guys? That right there should remind you of negative b plus or minus square root b squared minus 4ac all over 2a. It's in the same exact format as the quadratic formula. So anytime you guys see something like this where you're given a quadratic and a solution in the format of the quadratic formula, yeah, you can go ahead and use the quadratic formula, but a lot of students don't have it memorized, and it's also just really, really time consuming. So a much easier and funner way of doing this problem is I can go to Desmos and plug in my original quadratic. After I plug in my original quadratic, I'm going to get my 2 solutions, because you guys remember earlier, this is a 1 variable equation, and Desmos will directly give me the solutions, right? So I'll go ahead and I'll export both of these solutions. And since I'm told that the solution can be written in the format of 8 minus square root k over 4, well, I know that this is a solution, so this solution should equal one of these, right? So I'll go ahead and I'll plug that in. I'll plug in 8 minus square root of k divided by 4. And I know that 8 minus square root of k over 4 should equal one of these guys right here. So take this, copy, paste it over, and I'll do the same exact thing for the other solution, because it could equal one of the solutions, right? So at this point, I no longer need this. I've already got my solution. Let me get that out of the way. And I don't need these to like actually show up over there. So I'm just trying to keep my workspace clean over here. All right, now Desmos is not graphing these. Why not? We only support implicit equations of x and y. So I just got to go ahead and change my k to an x, because Desmos is a little confused right now as to whether I'm dealing with a constant or a variable. But if I put x, it now knows that it is indeed a variable. Nothing shows up. Oh, nope. Something does show up. It's not giving me the point, so I just need to zoom in. Once I zoom in, I get 120. So my answer to this one is 120. I could change this one too, but this one is not going to come out to anything. So this is green. And when I zoom out, there is nothing green. And a lot of students ask me, they're like, oh, why does it only work for one, but not for the other? Because the quadratic formula goes negative b plus or minus, and this is just minus. So this is just one of the solutions. So anytime you guys have any quadratic formula questions, you can solve it with Desmos. It's a little bit more efficient, in my opinion. Trick number 6 is on possible factors. These, again, are not that common, anywhere between 0 and 1 of these every single test. So this one will get you about an average of 5 extra points per test. So we are now at 100 extra points. So over here on math, which of the following expressions is or are a factor of this quadratic? So if you guys have a good conceptual understanding of what's actually happening over here, you guys can actually translate all of this over to Desmos. So if one of these would be a factor of this quadratic, I want you guys to think about what these factors would tell you. Well, when you know that one of the factors is x minus 3, then that tells you that one of the zeros of the graph would be x equals 3. Because, you know, you take this, set it equal to 0, just like some good old algebra 2, right? So I do the same exact thing for this one. If I take 3x minus 7 and I set it equal to 0, 3x equals 7, so x equals 7/3. So this will tell me that one of the zeros for this one would be 7/3. Now I want you guys to think about what the zeros are and what the zeros mean. The zeros of a quadratic are also your x-intercepts. So if these are my x-intercepts, let's think about that. I could just plug this in. I can find my x-intercepts because Desmos would give me the graph of this. And if my x-intercepts match up with both of these, then they're both true. Or if it matches up with just one of them, then one of them is true. So I'll go to Desmos, I will plug in my quadratic, and let me look to see where it hits the x-axis. It hits it at -9. -9 does not match with this one, so this one is out. And then it also crosses through 2.333. If you plug 7 over 3 into the calculator, that does indeed come out to 2.3 repeating. So 2 works, 1 does not. My answer is 2 only. This is a cool trick that you guys can use on the SAT in order to find possible factors, because we all know that factoring when the leading coefficient is bigger than 1 is just simply not fun and very time consuming. So this one is definitely a good trick. The 7th and final trick is on no solution and infinite solution system of equations. These are super common. There's usually about 2 of them every single test. So knowing this trick can easily get you 20 extra points, which would now put you at 120 extra points. So in this question, I'm given a system of equations. I'm told that P is a constant, and I'm also told that the system has no solution. So I need to find the value of P. So I want you guys to think about this. This is a degree of 1. This is a degree of 1, which tells me that both of these are linear. Now, the solution to a linear system of equations is going to be their intersection point, right? So if I'm told that they have no solution, what's that going to tell me about my lines? That's going to tell me that my lines are parallel, right? So what I can do is I can simply go to Desmos and I can plot both of my equations, and then I can just add a slider for P, and I can mess around with values for P until I get them to become parallel. And I noticed that right around there, they seem to be parallel, right? Now, what a lot of students will do right here is, you know, they'll stop right there at 5.9 because they look parallel. More often than not, it's going to be a very clean round number, so I would go with 6. But if you guys want to be 100% sure as to whether or not they're actually parallel, here's what you can do. I noticed that the blue one's on top. So what I'm going to do is I'm going to zoom out a lot, and then I'm going to zoom in somewhere over here on the right. And since the blue one was on top, then the blue one should still be on top. If it's not, then that means that they crossed at some point. But in this case, I noticed that the blue one is indeed still on top. And I can do the same thing if I go all the way to the left. I notice that the blue one is still indeed on top. Therefore, they never cross. Therefore, P being 6 did indeed get them to be parallel and have no solution. Like I said, these are super, super, super common on the SAT and one of the easiest way to get some fast points. And that's it. 7 Desmos tricks that can literally be the difference between staring at your SAT math section like it's written in ancient Shakespeare goblin language, or walking in like, relax, I have the calculator, I have the sauce, I am the problem now. If you actually learn these 7 tricks, you're not just guessing better, you now have a cheat code style system for some of the most repeated question types on the SAT. Table regressions, one variable equations, equivalent expressions, systems, quadratics, possible factors, no solution, and infinite solution system of equations. These are not random. These show up over and over and over again. So don't just watch this and go, wow, that was fire, and then immediately scroll to a video of a raccoon stealing Doritos. Actually practice these. Open Blue Book, open Desmos, run the plays. And if you want more help, join our free school community called SAT Strategy Lab. Inside, we have forums where you can ask SAT questions whenever you get stuck, free SAT courses, and free Friday group classes. So if you want more tricks, more strategy, and more help raising your score without losing your mind, click the link below and join the free community. I'll see you in there. Now, go ahead and abuse Desmos responsibly.